Okay, so in this video, this will be 1.7, how single bonds are formed in organic compounds. So, central concepts: to form 4 bonds, carbon must promote an electron. This is because carbon has only a limited number of valence electrons. So it promotes an electron from an s orbital to an empty p orbital. We'll see this graphically. Carbon forms bonds using hybrid orbitals through a process called hybridization. Bonding pairs and lone pairs stay far apart because of electron repulsion. These are all concepts from general chemistry. All single bonds are sigma bonds. That's an important concept as well. In orange over here, this is just something that we should all keep in mind, that in organic chemistry, as we add on more carbons, we have different compounds, of course. So we will first focus on methane. So methane is CH4, and as we know, methane can be represented with this Lewis structure here, or the perspective drawing here, where the hatched wedge means that the H is going out of the plane of your paper or the board, whatever medium that you are currently viewing. The solid wedge means it's coming out towards you, and then the lines are in the perspective, in the paper or the board, right? And we know that the bond angle is 109.5 degrees, and we know that this is called tetrahedral, right? This is tetrahedral, and it comes from the idea of a tetrahedron, right? A tetrahedron. And interestingly enough, a tetrahedron can be derived from a cube. A cube is just, it's a 6-faced three-dimensional square, basically, and it's literally just the opposite corners of the faces of the squares. And that's how you get a tetrahedron. It's the optimal opposite sides of the faces. So I thought that was very interesting when I figured that out. So we can go to our next slide. So this is where we can talk about how 4 bonds are formed in carbon when it only has 2 valence electrons. So we have our 2s, right, and then we have our 2p. Here's our valence electrons, right, 2 valence electrons. So what happens is, through this process called promotion, we have one of the 2s electrons gets promoted to this 2p orbital, right? So now these atomic orbitals can hybridize, right? They can now merge together in a way. And this was introduced by Linus Pauling in 1931. So we can now discuss this process in a little bit more detail. So we can look at this axis here, this y-axis, this is energy axis. So in hybridization, all of these orbitals become degenerate, which means they have the same energy. So we have 1 s orbital and 3 p orbitals. They merge together to give us 4 sp3 orbitals. And we have to remember, this is very important because it's going to come back all throughout organic chemistry, and it's going to have repercussions. So a hybridized molecular orbital, it has this particular hybridized molecular orbital, it has 25% S character. You can think of it like this: S1P3, 25% S character, 75% P character, because S1P3, this adds up to 4, so this is going to be 25% S, 75% P. And if you think of it, you have 4 atomic orbitals, right? You're mixing 4 atomic orbitals, so you're going to get 4 molecular orbitals. So the number of atomic orbitals you mix is the number of molecular orbitals you obtain. So like a p orbital, sp3 orbitals are going to have 2 lobes. The s adds to one of them and subtracts from the other. So you have one positive or in phase lobe and an out of phase lobe. And the larger lobe is the lobe that's going to form the covalent bond, right? So we can go on to our next slide. Great. So let's talk a little bit about the tetrahedral carbon and the tetrahedral bond angle. So the 4 sp3 hybrids, they adopt a spatial arrangement that keeps them as far away from one another as possible. We know that electrons all have the same charge and similar charges repel. So let's talk a little bit about the bonds in ethane, C2H6, or as represented here, CH3CH3. It looks like this. All the bonds are single bonds, or sigma bonds, right, as mentioned earlier. Carbon uses 4 sp3 orbitals. One of the sp3 orbitals of one carbon will overlap with an sp3 of the other carbon to form the carbon-carbon bond. And this will be graphically represented in another slide here. So these are going to be, here's one carbon, here's the other carbon. We have 4 sp3 orbitals, and they're going to overlap. As you can see, as the carbon forms a sigma bond with the other carbon, that's going to be sp3 overlap. And then the CH bonds are going to be s orbitals of the hydrogens overlapping with the sp3 of the carbon that is hybridized, right? So a typical type of problem that you might see would be explain why a sigma bond formed by overlap with sp3 is stronger than a sigma bond formed with S and P. And there are a few ways that you could answer this, right? So let's just change this. So if we have S and it's overlapping with an sp3, right? If I can even draw it properly. Right? If it's forming with this, you're going to have 25% S character and 100% S character over here. But so this would be this one. But if you have this sigma bond forming, you're going to have 100% S character and 0% S character, right? So the average between these is going to be 50%, and the average between these is going to be 125 over 2. 125 over 2 is what? 67.5? Hell if I know. 62.5. So there's more S character